Okay, this is 2.3, rates of change, velocity and marginals. And so there are the three targets of this lesson. Talk about average rate of change, how to use a derivative to find velocity, and how to use a derivative to perform what's called marginal analysis. So I think what would be best as you're viewing this video is I've got things pre-written. So, hit the pause button when you're trying to write something, hit the pause button, write things down, and then resume. So, moving on to our first topic, 2.3.1, finding the average rate of change of a function. We've discussed two types of rates of change already up until this point. We've got an instantaneous rate of change, which you can see on the left. On the right, comparing that to what we need to talk about, average rate of change. So here on the left, the instantaneous rate of change, that's what's found by performing a derivative, finding the slope of the tangent line. That's the rate of change at one particular point of the function, which is why we use a tangent line. Okay, and to find the slope of that tangent line, again, you do the derivative, and you can find that rate of change. It's an instantaneous rate of change. With the average rate of change, that's comparable to what we talked about a few days ago with a secant line. Average rate of change is between two x values. So here I've got between a and b. And the average rate of change would be the slope of the line between those 2 points. In this case, it would be a secant line. And the way that you find the slope of a line with 2 points is just using the slope formula, which I have written right here. Change in y divided by change in x. So you need to read through your homework problems very carefully and try to determine, are they asking for an average rate of change? Or is this going to be an instantaneous rate of change? And if it's an instantaneous rate of change, you're going to use a derivative at one x value. If it's an average rate of change, you're finding the slope between 2 points using the slope formula. So an example here, find the average rate of change of this function, x squared plus 3x minus 2, and the two x values, that's what this right here is. This is a range of x values between x equals 1 and x equals 4. So we need to use the slope formula. So f of x1 minus f of x2 minus f of x1 over x2 minus x1, where here we have x1 and x2. So we need to figure out what f of 1 is. We need to figure out what f of 4 is. So f of 1, it's 1 squared. I'm just plugging this into the function. 3 times 1 minus 2. It's going to be 1 plus 3. 1 plus 3 is 4. 4 minus 2 is 2. Now for f of 4, 4 squared plus 3 times 4. So we've got 16. 16 plus 12 minus 2. 16 plus 12 is 28. 28 minus 2 is 26. So we have 26 minus 2 over 4 minus 1. These are the two x values, x equals 4 and x equals 1. So we've got 24 over 3 and 8. So the average rate of change of this function between x equals 1 and x equals 4 is 8. application of instantaneous rate of change and average rate of change we can look at is the velocity of a falling object. So you may have seen a problem kind of like this in your Math 1050 course, where a ball is dropped from a certain height. The position of the ball at any given time t is given by a certain equation. So this is the equation we're going to be using. This is called the position function, where s is the height of the ball or the object and t is the time in seconds. And this is an equation you're going to want to notice and take note of. The position function. Oftentimes in a problem, the position function will be given to you to work with. There are some instances in your homework and possibly on an exam where, given some initial information, you're going to have to be able to create this position function. So it's important to note what these variables mean. This first part, the quadratic part, 16t squared, that's always negative 16t squared if we're dealing with feet and seconds. This is the effect of gravity in terms of feet per second. That's the acceleration of gravity. This variable right here is the initial velocity, and they'll give that information in the problem. For example, a ball is thrown upward with an initial velocity of 40 feet per second. Well, that's where you would put initial velocity right there. Now, this variable right here, h sub 0, that's the initial height. So if it's thrown at ground level and the ball is thrown upward from ground level, the initial height would be 0. If the ball is dropped from a certain height, that's where that value would go, is that initial height. Now, once the position function has been created, one of the questions are going to be asked on the homework and possibly in an exam is find the average velocity of the object from time equals a certain time value to time equals another certain time. So, for example, between 4 seconds and 8 seconds, what was the average velocity of the ball? Or from time equals 0 to time equals 3 seconds, what was the average velocity of the ball? Well, average velocity is the change in position divided by the change in time. This is just the slope of a line between 2 points, because this is like average rate of change, like average velocity. So we're just using the slope formula, using the position function, much like we did in the last example. If you are asked to find a velocity or instantaneous velocity, those are synonymous. The instantaneous velocity, or just velocity, is the derivative of the position function. Because a velocity is a rate of change, and a rate of change is a derivative. So here's an example. At time t equals 0, a diver jumps off from a diving board. The diving board is 12 feet high. The diver jumps with an initial velocity of 16 feet per second. So this particular problem, the position function is given for us right here. Part A of this is what's the average velocity over this time interval. So from time t equals 0 to time t equals 1, what was the average velocity of the diver? Well, we know at time t equals 0, the moment the diver is jumping off the board, it has an initial velocity of 16 feet per second. But because of gravity, the velocity is either going to increase or decrease. So of all those different moments in time between time equals 0 and time equals 1, we're trying to figure out what the average velocity. So we're going to use the function average velocity is just the change in position divided by the change in time. So we use the position function for this. So we need to know the position at 1 second, subtract the position at 0 seconds, divided by the change in time, which is 1 second minus 0 seconds. So plugging a 1 into the position function, that's going to give us, so I'm plugging a 1 into this function right here. We're going to add negative 16 plus 16, which is 0. And then 0 plus 12 is 12. Now for 0, if we plug in a 0 into the position function, we're going to have 0 plus 0, which is 0, and then 0 plus 12. So we get a 12 out of that one as well. So you think, well, how can they be at the same position? Well, you come over here and maybe draw this. Here we've got the pool. There's a diving board right here that's 12 feet off the ground. We got this little diver diving in. So this is 12 feet. At 0 seconds, the diver is 12 feet off the ground. The diver jumps, and then after once, the diver might go up a little bit, but after 1 second, the diver is the same height, 12 feet. So what it sounds like is the diver went up a little bit, and then after 1 second, the diver is again 12 feet off the ground. That's how I'm making sense of this value right here, that at 1 second and at 0 seconds, the diver has the same position. Twelve minus 12 is 0. 0 divided by 1 equals 0. So again, how do we reconcile? How do you have an average velocity of 0? Because the diver was obviously moving. So there has to be some kind of a velocity, and here's how we make sense of this. When the diver is moving up, at some point there's going to be the high point of this diver's trajectory, and then the diver has to move down. So this has to do with positive and negative velocity. When the diver is moving in this direction, there it goes. When the diver is moving in this direction, going up, it actually has positive velocity. When the diver is moving in this direction, the velocity is actually negative. And this is more of a physics discussion, but this has to do with point of reference. If you're moving away from the point of reference, it's positive velocity. If you're moving towards the point of reference, it's negative velocity. And because this took half a second to get to the top, and it took another half a second to get down to 12 feet again, those cancel each other out, which is why the average velocity is 0, meaning that the amount of positive velocity here is equal to the amount of negative velocity here. So when you add all the positives and negatives from here to here, since they equal each other, the average velocity is going to be 0, is what's happening. And more specifically, 0, since this is a rate of change, 0 feet per second. Now, part B is asking for the diver's velocity, not average velocity, but just velocity. So they're implying instantaneous velocity at time t equals 1. So that's v of t, which is the derivative of position. So if we look at the position function here and take the derivative here, using the power rule, which we talked about last time, the derivative is going to be negative 32t plus 16. So this is the velocity function, negative 32t plus 16. We want the velocity specifically at time t equals 1. So the velocity at time t equals 1 is negative 32 times 1 plus 16, which equals negative 16 feet per second. Now, how long does it take the diver to hit the water? So going back to this drawing here, it took 1 second. Let me clean this up a little bit. So here's the water, we got the diver, 12 feet off the ground. It took 1 second to go up and then down to 12 feet again. So this is 1 second. How much longer is it going to take for this diver to hit the water right there? So obviously more than 1 second. Now if we think about answering this question, we need to figure out the position of the diver right here when the diver hits the water. Okay. The position of the diver when it hits the water is 0, because the diver is 0 feet off the water. So essentially what we're trying to answer here is when does the diver let me try this again. When does the diver's position equal 0? So what we're trying to answer is this equation, because the position of the diver is given by the equation S of t, so we're trying to figure out the equation when does S of t equal 0. So we've got negative 16 t squared plus 16t plus 12. We need to solve this equation for 0. Now we have a couple different ways that we can solve a quadratic equation, because that's what this is. It's a quadratic equation. We can try factoring to see if that works. I'm going to factor out a negative 4. That's going to give me 4t squared minus 4t minus 3. And then factor this using some techniques of factoring. I've got a 4 here and a negative 3 there. So I'm going to multiply those two to get negative 12. And then I need to find factors of negative 12 that add to negative 4. So that's going to be a negative 6 and a positive 2. So what I need to do is rewrite this as 4t squared minus 6t plus 2t minus 3. So I've got 4 terms now. I can factor this one by grouping. From this first group, I can factor out a 2t, which leaves me 2t minus 3. From this group here, the only thing those two terms have in common is a plus 1. So that leaves me with 2t minus 3. So that factors into negative 4. Then I've got a 2t minus 3, 2t plus 1. So from this, my two values of t that is going to make this quadratic equation equal 0 are t equals 3/2 and t equals negative 1/2. Now, these are values of time. That's what t equals. It doesn't make sense to have a negative value of time. Time moves forward, not backwards. So what this is saying is after 3/2 of a second, the diver hits the water. Because after 3/2 of a second, the position of the diver is 0. So diver hits the water after 3/2 of a second, or 1.5 seconds. Now the question is, what's the velocity of the diver at impact? Well, the diver impacts the water at 1.5 seconds, so we need to find the velocity at 1.5 seconds. So what's the velocity at 1.5 seconds? We go back to the velocity function, which was here. This is the velocity function. This is negative 32 times 1.5 seconds plus 16. Make sure I got that. Plus 16, yep. So 32 times 1.5, that's negative 48. 16. So at the moment the diver is hitting the water, the diver is traveling negative 32 feet per second. And again, this velocity is negative here because the diver is traveling towards the water, towards the point of reference, gives them a negative velocity. Okay, the last part of the discussion for section 2.3 involves marginals and marginal analysis. It's an application of economics, and a marginal is a rate of change. And specifically, we're going to study rate of change of profit, revenue, and cost. So the rate of change of profit, the rate of change of revenue, and the rate of change of cost. First equation here you need to notice is that the profit is equal to revenue subtract cost, where X represents the number of units. And you'll see, you'll get a little bit more practice with this in your homework. So that's an equation you're going to want to memorize. The profit is equal to revenue minus cost. Okay. Now, marginal profit, marginal revenue, and marginal cost, like I said, those are instantaneous rates of change at a given value of X. So a company can calculate, let's say, profit, but if it wants to calculate marginal profit, or how profit is changing, or how revenue is changing, or how cost is changing, then we want to calculate a marginal profit, or a marginal revenue, or a marginal cost. And these are instantaneous rates of change. So that means we can find that using first derivatives. So given a function describing a profit, or given a function describing revenue, or given a function describing cost, we can calculate marginal revenue by calculating a first derivative. Like this one here, the derivative of profit with respect to X, where X is number of units sold. Or here, marginal revenue, the rate of change of revenue is the derivative of revenue with respect to X, where X is the number of units sold. Marginal cost, same thing, where X represents the number of units produced. So an example of what that would look like. The revenue from renting X number of apartments for a particular company can be modeled by this function, negative 2x cubed plus 64x squared plus 1800x. Find the marginal revenue when X equals 14. What is it they're asking us to do here? Well, X equals 14 means they're renting 14 apartments, okay? And they're wanting us to find the marginal revenue. So they don't want us to calculate the actual revenue if they're renting 14 apartments. What's the rate of change of revenue? Okay. So marginal revenue means dr dx. And we can find these derivatives simply using the techniques of differentiation that we've discussed so far. Product rule, quotient rule, simple power rule, chain rule, any of those that apply. This one, we can just do simple power rule. So we're going to have negative 6x squared plus 128x plus 1800. So now the marginal revenue at 14. So calculating this, we would get so plugging in a 14 into this marginal revenue function. Okay, and then hopefully you've got a calculator you can use to help you with this. So just give me a quick sec. So I'm getting $2,416. Now you need to be very particular and careful on how you answer this. Because this is a marginal revenue, that means it's a rate of change. It's an instantaneous rate of change. So because it's a revenue function, we know it's in terms of dollars, $2,416. But dollars per what? How is it changing? And you can look at how this is defined right here. dr means the derivative of the revenue. That's the numerator. The denominator there over dx is a change of x, and x is represented in units, x number of apartments, and it's a single 1 unit. So this is dollars per unit. Now we need to pause and reflect on what this means, this marginal revenue. It's one thing to find an answer, but it's another thing to understand what it means. So when this company is renting 14 apartments, the marginal revenue, meaning the rate of change of revenue, is $2,416. It's positive, meaning the revenue is going up, it's changing positively. But this is not saying that when they're renting 14 apartments, the company is earning $2,416. It's saying that at 14 apartments, this company is increasing their revenue at a rate of $2,416 per unit, meaning if they've changed renting from 14 units to 15 units, that's a 1 unit increase, they can expect their revenue to change by about this amount. And I say by about this amount because a marginal revenue is a close approximation to the actual change in revenue. And that's what part B is asking for, is find the actual change in revenue when the number of rentals is increased from 14 to 15. So they're having a 1 unit increase. So the number of units is changing by 1 unit, which is what's going on here per unit. So per 1 unit increase, we can expect that the revenue is going to change by about this amount. And so we actually need to calculate the revenue, not the change in revenue. So not using marginal revenue, we're actually using this revenue function here. So we need to calculate the revenue at 14 apartments and calculate the revenue with 15 apartments. And that's what I've done here. I've plugged 14 into the revenue function, and I've plugged 15 into the revenue function. And this is what we get from that. 32,256 and the 34,650. And if we take the difference of those, 34,650 minus 32,256, the difference is $2,394. So that's the actual change in revenue. If the company increases from 14 rentals to 15 rentals, we can compare that to the marginal revenue, which was $2,416, which estimated the change in revenue at 14 units for a 1 unit increase, and they're pretty darn close. So that's one reason marginal analysis can be so helpful, is rather than having to calculate actual revenues at different price points, they can estimate changes in revenues and profits and costs at a single price point using marginals. Okay, now one last little explanation here is a demand function. So we'll talk about supply and demand from time to time in this course, and it's important to have a working understanding of how to calculate and what demand is and how to use it. So the demand function is a function of x, and you got to notice this is a lowercase p and not an uppercase p. Uppercase p is for profit, lowercase p is for price, and it's a function of x. And typically it'll be a linear function like this. It doesn't have to be, but typically it'll be a linear function. And x represents the number of units that customers or consumers are willing to purchase. And this axis here, the vertical axis, p, is price, not profit, but price. And you'll typically see, at least for a lot of our examples, that the demand function is linear with a negative slope, meaning if they raise the price, they sell fewer units because the price is raised. It's kind of how you can think about that. And with that, revenue is a function of price multiplied by number of units. If a company wants to say, well, how much revenue did we make today? Well, they need to first figure out how much product they sold. Okay, that's the number of units sold right there, x. And then they need to figure out, well, how much did they sell it for? So multiplied by a price. So revenue equals x times p, number of units sold multiplied by the price they sold the units for.